Okay, let's get started. This is my marketing slide. There's just a bunch of information there about things that I've done in the past, and well, pretty much you can Google any of this information if you're interested. But the highlights are co-founded JClarity. We built a lot of performance diagnostic tooling, and just last year Microsoft acquired us, and so now I'm a principal engineer within Microsoft. Let's start with a demo. I'm just going to demo a small application. Let's start by looking at this game simulation, Mastermind, for those of you who might be interested. I'm just going to run it here. I'll have to drag it onto the screen so we can all see what's going on here. Normally we use colors. In this case I'm going to use numbers just because it's simpler and it provides us with a much bigger solution space. The point of the game is I'm going to give the computer a sequence of 3 numbers chosen out of 100,000, and it has to guess them. So let's just run this. You can notice that it's taking a bit of time to actually reach a solution. And if we want this thing to go faster, the question we have to answer is, what's slowing it down? So let's go into the presentation to see if we can get some hints as to what we can do to figure out what's slowing this application down. The question is, what is your performance trouble spot? In a live audience, face-to-face, normally we do a poll of hands and we get some idea of what people think their performance spot is. Unfortunately, we're in this situation with COVID, so it's not so easy to do. That's okay. We have some data here. This is a data taken from an industry survey. This is Rebel Labs. They've been acquired also now. So the people who did the survey, they went out to, they just went out and they said, just tell me what are the typical root causes of performance issues that you run into? And you can see, we see the usual suspects here, right? Like database, 54.8%. Too many database queries, 38 point, inefficient application code 51. So these are pretty much, all of the things that you would expect to show up. And that's because we have this bias in us, and this bias is telling us that these are actually the issues that we would expect to face, and this is the issues that our tooling is telling us that we're going to see, but and our logs are telling us, and this is all this data we're collecting is heavily biased from what we've actually seen in the past or what we think the actual issues are. In our experience, from looking at data from systems, we see excessive memory churn as being the issue. And you might look at the whole thing and say like, whoa, wait a second, but that only says like 10.56% of people are claiming that they've seen memory churn as an issue. Well, our claim is that somewhere around 60-70% of the applications that we've run into are bottlenecked on memory. And no, this is not a problem with garbage collection. So the garbage collector is not at fault. So the question is, do you use Spring Boot, Cassandra, or any other big NoSQL solution for that matter? So we don't want to pick on anything in particular, right? Apache Spark, the big data solutions, right? Or any of the big data frameworks, Log4j, any Java logging framework for that matter. Do you use a lot of JSON? In this crowd, probably the answer is yeah, you use it like all over the place, right? So, does JSON really matter? And well, we get the same problems with almost any marshalling protocol that you actually use. Ecom caching products, Hibernate, and the list goes on and on and on and on. And the thing is, if you're using these things, you're very likely in the 70%. So the question is like, if you're in the 70%, why don't you see it? And again, it comes back to the biases in our tools. We only see what we look for. And when we see something, of course, we're going to act on it. We're going to say, and we're going to get some improvements But generally those improvements are like 5 or 10. You know, maybe you do something really wonderful and you get like 20 or 30% performance improvements. The memory issue is so huge that when you actually start solving that issue, you get integer multiples of improvement in performance. So this isn't the typical 5 or 10% thing that you normally see on a full-scale application. It's like 1x, 2x, and in some cases we can see from the war stories here that we've been able to get like a 4x improvement in performance. And that's just huge. Just absolutely huge. And you can see the stories here, like 400,000 TPS to 25 million TPS by taking allocation rate down from 1.8 gigabytes per second, in this case, to 0. Kind of a special case, but even so, you can look at that. There's many multiples integers of performance improvement. Even when we're at low allocation rates, we had that to 6 to 7 million transactions per second. And I think that this whole story ties into the cloud deployments now, because we've been talking to some people who are trying to figure out, okay, like how do I help my customers actually densify their applications so that we can get more into the memory that we have. And one of the things that consistently prevents us from actually being able to densify applications on the hardware is simply the allocation rate. It's possible to have a single thread in a single JVM running on a piece of hardware, and if it's possible, if that thing is allocating hot, it's going to fill up the back end of the chip while the chip, the CPU is trying to write data out to memory. And if that gets backed up, then what happens is that the whole chip gets slowed down. And this is a chip. So it's not your JVM is slowed down. It's the chip gets slowed down, which means that, yeah, your JVM is going to be slower. And guess what? Everybody else's JVM running on that piece of hardware is also going to be slower. And this is a huge factor in what we call the noisy neighbor problem, which I imagine you guys are all very familiar with. So what's going on here? So, what's going on here and what can we do about it? Essentially what we're looking for are these things, right? So in this case we have foo equals new foo, and you can see in the bytecode it's like, we're going to create this new class, and we're going to do this in invoke special, which basically calls the constructor and everything like that. But effectively what all this does, it's going to allocate memory in Java heap. Now this can actually happen in a number of different ways. We can go down a fast path, which is one way. We can go down a slow path, which is another way. And maybe the best way is that all of a sudden we could have these allocations optimized so they don't even go on the heap, so that we end up with a scalar allocation or an inlining of the values as opposed to having them being allocated on heap. You look at these things and you say, okay, fast path is very cheap. The slow path is not expensive. It's still very cheap. It's just slower than the fast path, right? So what's going on here? Well, what's going on here is we have a frequency issue. The cost of allocating a large object is mostly equal to the cost of allocating smaller objects. So the cost of allocation is not based on the size. It's based on the frequency, because even though each one is cheap, a cheap times a lot equals a lot. And that's just the way it is. What we can do, and what we did do, and when we looked at the Mastermind application, is we used Sensum to give us an approximation of the allocation rate, and then we used that information to make the determination that this application is memory inefficient. So what are the rates that we're trying to look for? Well, here's a little chart. This is a little bit done by experience. And this is what we see, that the size of the gain is basically on some form of a power curve, and if you're above 1 gig per second, you have good opportunities to reduce the allocation rates and get some significant improvements in performance. By the time you get down to the other end of the tail, then of course, the opportunities become much smaller. So we'll look at an application and we'll evaluate its allocation rates, and we'll say, okay, based on that data and some other input from other things, we'll likely choose that, choose the path that we need to reduce the allocation rates in this particular application, the allocation frequency. So the effect on performance isn't just simply, it's not just simply about the cost of the allocation. It's also about everything else that goes around in terms of how memory is managed inside the JVM. Here's like just a extremely 10,000 foot view of memory management in the JVM, just to remind us of what this looks like. And you can see that the Java heap has an Eden space, a survivor space, and some tenured space, right? So the Eden is our nursery. If we look at what happens in each of these spaces, then you can see that, okay, that they each contribute to a different problem, but all of the problems that you encounter here are going to affect GC overhead. Application threads are going to allocate an Eden. Okay, so we really want to focus our discussion on what happens here, because this is the important thing, and this is the thing that we can have the most direct effect with our application code. If we play out an allocation here, you can see that here we have two threads that are both executing bits of code, and we have this buffer, this big heap, and we have a top of heap pointer. So what I'm going to do is I'm going to start executing the code here. So the first thing I'm going to go foo equals new foo. So I'm going to figure out, okay, how big is foo, and then I'm going to grab that amount of memory off of the heap. Now if I keep doing that, of course I'm going to have a hot pointer, because how this works is that to get the memory, I'm just going to do what's known as a bump and run on this top of heap pointer, right? So if I got multiple threads trying to do allocations, then they're all contending for the pointer, and that's an issue. So we're going to introduce this other data structure known as a TLAB. So when I go to heap, what I'm going to do is I'm going to grab a TLAB, and that starts off as being a megabyte in size. So now I have an internal pointer. I know that this is from my thread, so basically what I can do is I can grab the memory I need, fill in the data, and that's our allocation. So if I go to the next thread and I say, okay, bar equals new bar, what I'm going to do is I'm going to go out, grab a TLAB. Internal to that TLAB, I'm going to grab the memory I need, and then I'm going to fill out the data. Now the next thing to execute is this byte array equals new byte. So let's say we get a big one, bigger than a megabyte, so it doesn't fit into the TLAB. So how's that going to work? Well, in this case, I'm going to have to allocate outside of a TLAB. So what I'm going to do is I'm going to bump the top of heap pointer, grab the size of the array, and then I'm going to fill in the data. If things are small and they fit in the TLAB, as you can see, life is going to be good. If things are bigger and they don't fit in the TLABs, then life is going to be a little bit more expensive. Okay, and that's generally the rule of thumb that you can have with all of the collectors. Small are going to be managed fairly cheaply. Larger are going to be managed in a slightly more expensive way. Okay, but the cost of the actual allocation is really not that much different. Again, it's the frequency that's going to trip you up here. Now, there is a few details here, like what happens when you get to the end of the TLAB and you don't have enough memory, and there's some waste conditions and things like that that you have to look after. So if you get this right, then your allocations are going to be really fast, and if you don't get it right, then of course you're going to get some allocation failure, and then you have to do a retry, and the retry is going to get a new TLAB, and so there's some mechanics here that happen, but let's just say that these become more of a minor concern, with the exception that when we get into high allocation rates, then of course even these things happen more frequently. Tenured space, with the generational collectors, we're going to have a free list. With G1, of course, it's a regional collector. The mechanisms are going to be different, but there's still extra work that you have to do here. in both cases. In the generational spaces, that means that we need to manage the free list. And managing the free list actually works out to be a lot more expensive than just doing a simple bump and run. And the data in tenured, though, tends to be long-lived. So there's, and most of the data from what we know is generally very short-lived. So most of the data should never make it into tenured. So the fact that it's more expensive to deal with tenured shouldn't really be an issue. Shouldn't. But with high allocation rates, it certainly can be. So let's look at the problems, right? So we have high memory churn rates. That means we're going to have memory and many temporary objects. And so what this means is that we're going to quickly fill Eden. We're going to have frequent young GC cycles. That speeds up the aging process. So data is going to be moved from young into tenured space based on how many collections it survived. So think of it this way. If I have data hanging around for 30 seconds, the question is that data still in young at the end of 30 seconds, or is it in tenured space? And the answer is, well, I guess it depends on how frequently the collector is running. Well, how frequently is the collector running? Well, if we have high allocation rates, then it's generally running a lot faster. And that means we've sped up the aging process. It means that data that might be in young gen that's cheap to collect is now sitting in tenured space where it's a lot more expensive to get it there and it's a lot more expensive to collect. This is known as premature promotion. And with lots of premature promotion, well, guess what? You fill up tenured faster, so you get more frequent collections of tenured, and increased copy costs, increased heap fragmentation, and so on and so forth. So you can see that having all this temporary data end up in tenured space is really not a good thing to do. And again, allocation is quick, but again, quick times a large number equals slow, and you can see there's these other after effects that this thing is responsible for. It's going to hyperactivate the garbage collector, and everyone's going to blame the garbage collector. I mean everyone. But it's not really the garbage collector's fault. But the garbage collector generally takes the blame for this. Another problem, large live dataset sizes. And no, this is not an advertisement to go off HEAP. I know going off HEAP was very popular for a period of time, and there's lots of products there that go off HEAP. But when you go off HEAP, you're going to get a larger live dataset size in Java HEAP, but that means you're marshalling to byte buffers off HEAP, and then you're marshalling to from the byte buffers off HEAP back into Java HEAP. And remember we said marshalling was a cause of high allocation rates? So guess what? You're trading this intermittent tail latency issue for a high allocation rate issue. So something that's intermittent and localized now is evenly distributed and global. Okay. With the large live dataset size, we have inflated live dataset size. You can inflate this by a number of different means. We can go through the list, but effectively, we can inflate a scan for root time. So when we do our scan for roots, that's finding our live objects that create the set of data that we start our mark cycles from. So we need to scan in a whole bunch of different places to find them. One of them is tenure space. We get reduced page locality. So this is how likely is related data going to end up on the same page? Well, in this case, it's likely less. We get inflated compaction times, increased copy costs, and less space to copy to generally if we've undersized our heap. So there's all kinds of issues that come with here. So take a look at this chart here. You can see on the left I have occupancy after collection. So if you look at the red line thing at the bottom, it's not really a line, but it sort of forms a line. And on the other side, what we have is pause times. So bigger live set, more work for the collector to do, longer pause times. So smaller heaps, in this case, are a solution But again, going off heap can cause more issues. So it's a quandary, shall we say, as to what to do. And of course, we can have an unstable live set, which is essentially a memory leak. And, you know, hitting a memory leak is never a really good idea. Let's take a deeper look at Mastermind and investigate how we can improve the performance of this little application. And I'm going to start running it. There, we're running the test. What we're looking to do is try to find out what the primary bottleneck is. Now, we've already seen that the CPU is running hot, so that just leaves us the question, is it running hot because of some algorithmic complexity, or is there some memory inefficiency that we need to look at? So let's just collect the run here. We'll get a baseline timing, and I'm also collecting a GC log. We'll perform some analysis on the GC log to make that determination. We're at the end of the run. It's taken 74 seconds to reach the conclusion. So now we can take a look at the GC log. Let's open it up and look at the summary information. We're at 98.7% efficiency, which is pretty decent. We're running a collection. The rate is about 1 every 6 seconds, which is maybe a little quick, but it's still pretty reasonable. If I look at my heap occupancy, I've accumulated a little bit of memory. That's expected, but memory is stable. Heap looks reasonably sized. Then we look at the allocation rate, and we can see our allocation rate is way above our 1 gigabyte per second threshold. It's running about 7. So this is putting a lot of pressure on the back end of the chip, as the chip is trying to keep up writing all of this data out to memory. Our next step then would be to find the hot allocation site or hot allocation sites that is responsible for all of this data creation. We'll take a look to see what we can do to quiesce that or quiet it down. So let's quit here. I'm going to use Visual VM. Now there's a number of other tools I could use. Could use Flight Recorder. And it's very likely in this case Flight Recorder would work very well. But in this case, the tooling doesn't really matter that much. What matters is to understand what the tooling will find for you, how much information the tooling will give to you, and more importantly, what the tooling is blind to, and what type of false positives the tooling will give you. So all tooling will be subject to some of this, and Visual VM is no different. So if I look here, I went into the profiler and I've set up the memory settings, and I can see I've set up my filters to just give me everything. And the reason it's giving me everything is because I don't know what I'm looking for. So I don't want the filters to actually filter out things that might be interesting to me. So let's go and attach our memory profiler under these conditions. And if we look at the data that's being collected, well, this is the name. I'm going to start the run here. We can look at the rest. So you see the data that's being collected. It's the class, number of live bytes, number of live objects, number of allocated objects, and generational counts. Generational counts is a long discussion for another talk. Now, I'm not interested in live objects or live bytes for that matter. In this case, I'm really interested in the allocated objects. I don't have a allocations per second count here, so I don't really have a frequency, but I can use this as a proxy measure for that. This is an approximation of what I'm looking for. And so very quickly, we can see that the int array is at the top of the list. And normally we just wait a little bit to watch the profile develop, because sometimes the mode of operation can shift, and when the mode of operation shifts, then it's quite possible that you're going to expose a new or different bottleneck than the one that you had when you're operating in the first mode. In this case, it looks like we have a lot of int arrays, so I'm going to snapshot that. We've been running long enough. Again, I'm going to sort by allocated objects. And if we look at where the int array is coming from, I'll just open this up. And we have a mutable big integer. And this is coming from a arrangement group calculate element index. We can open up this, and you can start seeing that, okay, now we have a clue as to where in the code we have to go look to see why we're creating all these int arrays, well, why we're creating all of these big integers. While we're here, I'm going to take a look at another class, and that's going to be this score object. Let's see if we can go over the profiler and see what's happening here. Okay. If we look at the score object, eventually this score is going to bubble right up to the top. So this is going to be the hot allocator. And if I look at this allocation path, you can see that it goes through this thing, board is possible solution. So before we tackle this main problem, let's take a look at this score object, because this is an interesting case. If we go into the source code, board, we can look at is possible solution. That's my allocation spot right here, score equals new score, and you can see it's in a loop. I'm just banging on this allocation site, just going new score, new score, new score, new scores, right? And that's just going to add up and create a lot of pressure. But is this real? And the answer is no, it's not, because if we look at score, we're going to see that it's, well, a Boolean and 2 ints. So this is a very, very small object. And what the optimizers are likely to do with this particular object is to scalar replace this allocation site. And that means that instead of new scores being made, you're going to get code that looks something like this. Not exactly, but something like this. In other words, we're going to allocate the space for the score object, and then I'm just going to reuse that memory over and over and over again. And of course, I could have written the code like this in the first place, or if I believed the profiler, and I believe that this was actually an allocation hotspot, then I might go in and rewrite the code this way. But in this case, I know that the JIT compiler is going to look after this problem with me. Now, it won't always look after this problem. So you still can have hot allocators in loops, and that still can be an issue. But in this case, I know the JIT compiler is going to look after it. I've taken the JIT compiler logs and examined them to figure out what's going on here. Why? The profiler is instrumenting the code, and it's passing the score object into that code, and a second thread now has access to the score object. And under those conditions, we can't do the scalar replacement. Therefore, we have to allocate. Okay, let's go back and look at, there we go. Go back to the profiler. Let's see, the score object has bubbled up, and it's going to continue to bubble up as the profile develops. So if we go back to the int, so we had a big mutable integer, and it went all the way down into this arrangement group calculate index method. So let's go take a look at that. Now, this code is a bit complicated, so I don't really want to dive into it too deeply, but what it's doing is it's converting a index into one of these 3-digit numbers here. So the 0, 7, oh, you can pick one number combination, and this is what the program is offering the board to score. So it's going to score it against this. So if we come back and look at this code, we can see that there's all kinds of places in here where we're actually doing a lot of maths to figure out things, and we have this other method down here, remove symbol, which is creating new interarrays. So interarrays are being created pretty much all over the place here. So you can see the interarrays is a key element of the calculations here. What I'm going to do is I'm just going to quickly swap this out for a more efficient implementation. So we figured out that creating interarrays was a problem, so let's come up with an implementation that doesn't do this. And we can exit the program. Going to exit Visual VM. So we've gone in and we've identified the problem, we've made the change to the code. The next thing to do is to re-baseline this. Going to run the test. And you can see it's running much faster than it did before. And now we're running in 11, almost 12 seconds. If we go back and look at the GC log to see what the memory picture looks like. Open it up. From our summary, we're at 99.4% efficiency. We're running the collections at a much higher rate. Memory is stable, and our allocation rates are way down. They're now below our 1 gigabyte per second threshold that we set. If we want to make this thing even faster, it's very likely the next bit of work we have to do will not involve reducing allocations. There's this chicken and this pig. They're hanging out in the barnyard and they're having a good time there, and finally the chicken goes to the pig and says, "We should start a breakfast place. I think that would be a really good idea. It'd give us something to do. We can make some money. It's great. We just serve breakfast food, right? Bacon and eggs, pancakes, waffles, breakfast stuff." When the chicken started listing the menu, the pig's eyes got a little big, and he's thinking about this. And finally he goes to the chicken, he says, "No, I don't think I want to do that." And the chicken says, "Why not? It's a great idea. You'd be good at it." And the pig says, "No, I really don't want to do it because, chicken, you're involved, but I'm committed." In this story of allocators and garbage collections, the allocators are involved, but it's the garbage collector that's committed. So why is the pig committed? Well, if you look at Eden And let's say that we have its size to be 2 gigabytes. And let's also say that we have this 1 gigabyte per second allocation rate. If you do the math, that means we're going to end up with 1 GC cycle every 2 seconds. And in my books, that's a pretty hot running collector, and I'd certainly want to slow it down. I want it to run once every 10 seconds or once every 20 seconds, something far away from 2 seconds. And so if I look at this problem and think, okay, what do I got to do to slow the collector down? I really only have 2 levers that I can pull on. The first is the allocation rate. That's the chicken. And if there's nothing I can do about the chicken, then I got to deal with the pig. And the pig is, I need to make Eden bigger. And if we come back to how this affects cloud deployments, if you think about the expense of resources, memory's right up there. So every time I have to make the heap bigger, that's going to cost more money. If you work backwards from that, every time I increase the allocation rates in my application, I'm costing money because I also have to increase the heap size in order to have the garbage collector cope with what the allocators are pushing on it. So that makes this, in my opinion, a fairly important thing to look at when you're evaluating your application. What are the allocation rates? And think about this from an observability point of view. What do you have in your production system that's allowing you to assess the allocation rates of your application? And that's it. Okay. Thank you for watching. And at the time of recording this, I'm not sure what the Q&A situation is like, so I assume I'll be around for a Q&A. Thank you.